All right, and we're rolling. All right. All right. Good afternoon, everyone, and welcome to our lesson on minerals. Now, if you'll start the PowerPoint presentation here, we can move on to slide 2. Is where we're going to start today with elements and the periodic table. Elements are the basic building blocks of minerals. Over 100 elements are known. If you remember our lesson on the periodic table, we talked about many of these elements, from carbon, oxygen, sodium, potassium, aluminum, iron, cobalt, nickel. However, in our day-to-day life, we don't often see these elements by themselves. If you walk outside and look on the ground, you are probably not going to find any elemental aluminum or elemental sodium just sitting there. In nature, these elements bond to each other to form new compounds. For example, some of the simple compounds that we've talked about, we all know water is H2O. That's a compound of one oxygen atom and two hydrogen atoms. We also know carbon dioxide, which is one carbon atom and two oxygen atoms. Within these compounds, many compounds are known as minerals. And the purpose of today's lesson is to help you understand which elements are known as minerals and how they form and why they look the way they do. So let's move on. Here we are on slide 3. To understand minerals, we have to understand a little bit about the atoms themselves. The atoms that make up these minerals, their molecules and their crystals. On slide 3, we see that atoms are the smallest particles of matter, but they have all the characteristics of an element. What is a characteristic? That means what it looks like, how it behaves, how it acts, especially with other elements. For example, so all of its chemical properties are going to be the same. An atom of oxygen will always bond with the same way with hydrogen or iron. An atom of carbon will always bond the same way with oxygen or with itself or with hydrogen. So its chemical properties are always going to be the same. Also, it's always going to look the same. Sodium vapor is always going to be the same. Oxygen is always going to look the same to us. Magnesium is always going to look and act the same. Within that element, within the atom, we actually have a pretty complex picture there. In the very center of the atom, we have the nucleus. We see bullet point 3 there on page 3. The nucleus is the central part of an atom. That means it's at the center of an atom, right in the middle. And it contains protons, which have positive charges, and neutrons, which have neutral charges. I know it can be difficult to understand this concept of charge, but what's important to take from this is an understanding that a positive charge and a negative charge are always going to attract one another, much the way the north end of a magnet attracts the south end of a magnet. Yeah, sure. Oh, okay.
So that's why it looks a bit messed up like that.
No problem.
We're rolling again.
And we're rolling. All right. So we've got. Oh, all right. I think we had a little interruption there. We have our protons with positive charges, neutrons with neutral charges. I know it's difficult to understand this concept of charge, but what is important to take from this is that two particles with opposite charge will be attracted to one another. A positive charge and a negative charge will be attracted, just as the north pole and south pole of two magnets will be attracted. And two like charges are going to repel each other. So two positive charges will repel. Two negative charges will repel. But a positive and a negative charge will be attracted to one another. There will be a force of attraction. All right. In atoms, the protons and the neutrons are all together in the nucleus, that very small, very dense part of an atom in the center. Now, around that nucleus is this much larger space where we find the atoms. On slide 4, we see that where we find the electrons. Those electrons are found in different energy levels or shells around the nucleus. As we go, all right, and here let's look at the next point. The atomic number is the number of protons in the nucleus of an atom. For example, hydrogen's atomic number is 1. A hydrogen atom will always have 1 proton. Oxygen's atomic number is 8. An oxygen atom will always have 8 protons. Now, most of the time, an atom will have the same number of protons and electrons. So we have the same number of positive charges and negative charges. Now those electrons are found in the space outside the nucleus. But they're not just moving around randomly. They are found in very specific areas, and they're found in a very certain pattern. In an electron, we see different energy levels or shells. We see that they're in bullet point 1 on slide 4. As we go from element to element in the periodic table, and we add electrons to the atom, they fill those shells starting with the smallest and lowest energy shells. For example, hydrogen and helium will only have electrons in the first shell. And it is only after that, as we move on to the larger elements, that we start to fill the larger and more high energy electron shells. In slide 5, we can see a pretty good picture, a pretty good model of the atom. Notice that nucleus, the red and blue part, that's where we have our neutrons and our protons. Those purple spheres around the nucleus are our energy levels. So you can imagine the electrons filling those energy levels one at a time. They start with the first energy level, and electrons will not start to fill the second energy level until the first energy level is completely full, until there's no more room in that first energy level. This is making it a little bit more complicated, is the fact that every energy level can actually hold a different number of electrons. And that's actually why the periodic table takes the shape that it does. But we will talk more about that later. Let's move on to slide 6, isotopes. Isotopes of an element have the same number of protons but varying number of neutrons. That just means a different number of neutrons. For example, helium will always have 2 protons. However, helium can have 0, 1, 2, or 3 neutrons. So the number of neutrons can change, but the number of protons, of positive charges, will always be the same. Because they have a different number of neutrons, they have a different mass. Because remember, our mass number is the sum of neutrons plus protons. Remember our lesson on the periodic table. Atomic number gives the number of protons. Mass number will tell us protons plus neutrons. Many isotopes are radioactive and emit energy and particles. The mass number is the number of neutrons and protons in the nucleus. All right. Remember, I said earlier that electrons moving around the nucleus of an atom fill the different shells. So we have energy shells, electron shells on the inside and outside. Now that outermost energy level is going to determine the way an atom will bond to other atoms. You can see here, when an atom's outermost energy level does not contain the maximum number of electrons, the atom is likely to form a chemical bond with one or more atoms. A compound consists of 2 or more elements that are chemically combined in specific proportions. As an example, let's take our very simple compound of water. In water, we have 1 atom of oxygen. Now, what do we know about oxygen? We know that its atomic number is 8, meaning that it has 8 protons in the nucleus and 8 electrons surrounding that nucleus. Now remember, I told you that first shell, that first electron shell, the inside electron shell, can hold 2 electrons. So in an oxygen atom, 2 electrons are on that inside shell. So that leaves 6 electrons. So there are 6 electrons in the second shell. However, that second shell can actually hold 8 electrons. So in oxygen, there are there are 6 electrons in a shell that can hold 8, meaning that there is room in that second shell for 2 more electrons. And that's why oxygen forms a bond with 2 atoms of hydrogen. Let's see. All right. So, yeah. And that's why these elements are always going to be combined in the same proportion. Oxygen will never bond with 3 hydrogen atoms. It will never bond with 1 hydrogen atom. It's always going to bond with 2 to form a water molecule. I want to look at that last point there on slide 7. An ion is an atom that gains or loses electrons. This is quite common. Remember that the protons in the nucleus have a positive charge, and the electrons in the shells have a negative charge. So if an atom gains an electron, if it gets 1 more electron, it will have more electrons than protons, and so it will have more negative charges than positive charges. So it will have an overall negative charge. If an atom loses an electron goes away, then we will have more protons than electrons, so more positive charges than negative charges. So the overall atom, the whole atom, will become positively charged. All right, so let's look on slide 8. Types of chemical bonds. Ionic bonds form between positive and negative ions. We've talked about this in a previous lesson. A very good, simple example of this is salt, sodium chloride. In a sodium chloride bond, a sodium atom will lose an electron. So the sodium will have more protons, so it will have a positive charge. The chlorine will gain an electron, so it will have more electrons, so it will have a negative charge. Well, now the positive sodium is attracted to the negative chlorine. So sodium and chlorine form an ionic bond, sodium chloride, which we know as table salt. Covalent bonds form when atoms share electrons. A good example of this is water. In a water molecule, the hydrogen atoms and the oxygen atom are sharing electrons, so that the hydrogen atom has 2 electrons in its shell, in its electron shell, and the oxygen atom has 8 in its electron shell. And number 3, metallic bonds form when metal ions share electrons. All right, let's move on. Our definition of a mineral. They are naturally occurring. That means they are not made by people. They are made by nature. We find them on the earth. 2, they are solid. So carbon dioxide and water are not minerals. Remember, carbon dioxide is a gas. Water is usually a liquid. So it is not. They are not minerals. Number 3, they have an orderly crystalline structure. That means that the arrangement of the atoms repeats. They're arranged in a specific pattern. The atoms are not just thrown together. They have a consistent repeating pattern. They have a definite chemical composition. They're always made of the same elements, and they are organic, meaning they do not have carbon. How minerals form. Number one, the crystallization from magma. Remember, magma refers to liquid rock that's buried deep in the earth. Remember, closer to the center of the earth, the pressure and the temperature are very high, so that the rocks will actually melt and become a liquid. That liquid rock is called magma. This is what we see coming out of volcanoes when they erupt. Minerals form from the crystallization of this magma. Right? Here on the next page, slide 11, we see a few minerals that are formed from the crystallization of magma. Many of these probably look like the rocks you can see every day. A few. Here. Minerals, on slide 12, minerals can be classified based on their composition. That means based on the elements that are in that mineral. Our first group, silicates. Silicon and oxygen combine to form a structure called the silicon-oxygen tetrahedron. I'm going to draw you a quick picture of what a tetrahedron might look like. Yeah, a structure like this. Imagine 4 triangles together. One's making 4 triangles. A tetrahedron. All right. This silicon-oxygen tetrahedron provides the framework for every silicate mineral. A few examples of this. Feldspar and quartz, which are the most common minerals on the planet, both have this pattern. Quartz is very, very simple. It is nothing but silicon and oxygen. You can see a picture of this tetrahedron on slide 13. We see that little blue circle in the center is the oxygen, and the 4 large brown atoms surrounding that oxygen are the silicon. Boom. Silicon-oxygen tetrahedron. There we go. There. On slide 14, we can see some silicon-oxygen chains, sheets, 3-dimensional networks. These silicates form a lot of different patterns. So from a very simple beginning of just silicon and oxygen, we can get a lot of different patterns, a lot of different shapes, depending on what other elements are present. All right. Another group, the carbonates, minerals that contain carbon, oxygen, and other metallic elements. In a carbonate, we see that's when we have carbonic acid, which is carbon with 3 oxygen atoms. It often bonds to metals like iron, or with alkali metals like sodium. So we get compounds like iron carbonate, sodium carbonate, and then the final group, oxide. These are minerals that contain oxygen and other elements which are usually metals, like iron oxide just one iron atom and one oxygen atom, iron oxide, which we commonly know as rust. Other groups, sulfates and sulfides. These are minerals that contain sulfur. Halides, minerals that contain halogen ion plus one or more other elements. Remember, the halogens are the elements that are over on the right side of the periodic table, right beside the noble gases. They form a lot of ionic bonds because they all have one space left in their valence shell, in their outermost shell, so they want to gain one more electron. So they gain electrons very easily, and so they form negative ions, which will then bond with positive ions. When this happens, we get the halides. And number 6, native elements, minerals that exist in relatively pure form. On the next slide, 17, we see examples of sulfides. The one on the left, here we go. That is iron sulfide, commonly known as fool's gold, because you can see the color. It looks very much like gold. Slide 18, native copper. This is, remember, 2 slides previously we talked about native elements, minerals that exist in pure form. An example would be native copper. This is copper in an almost pure form, that is, only copper. Some of the properties of minerals. The first one we're going to talk about is color. Now, small amounts of different elements can give the same mineral different colors. For example, feldspar, which is the most common mineral on the planet. It is a silicate, meaning it always contains silicon and oxygen. However, different samples of feldspar contain different amounts of other elements like magnesium or iron or aluminum. And when these different elements are in different amounts, they can give the mineral different colors. So even if it's still feldspar, it might have a different number of iron atoms in that crystal, and it could give the feldspar different colors. Streak is the color of a mineral in its powdered form. Luster, used to describe how light is reflected from the surface of a mineral. We understand this. How shiny is an element? When we saw a few slides earlier, when we looked at iron sulfide, the fool's gold, the reason people often mistake that for gold is because it has such luster. It's very shiny, like gold. Other elements like feldspar, for instance, is not shiny at all. It has almost no luster. Here on slide 22, you can see that pyrite, fool's gold, displays a metallic luster. It's the same color as gold, and it's very shiny, like gold. The crystal form is the visible expression of a mineral's internal arrangement. If you go back and look at the previous slide, you can see in that pyrite on slide 22, you get those straight lines going up and down in the pyrite. That's because of that crystal pattern of the pyrite, that arrangement of atoms that's constantly repeating. Here, on the next slide, 24, quartz. quartz exhibits a very good crystal form. One of the reasons that quartz makes such nice crystals is that quartz is very simple. It's only silicon and oxygen. So there is no iron or magnesium or sodium or aluminum or any other element present. It's just silicon and oxygen. So that pattern of silicon and oxygen will always repeat with no interruption. So it will always be the same. So it makes very nice, very straight, regular crystals. Moving on, slide 25, more properties. Hardness. That's a measure of the resistance of a mineral to being scratched. We measure hardness on the Mohs scale. We go from 10 to 1. We can see that on slide 26. Notice up there at the very top at 10 we have a diamond. A diamond is elemental carbon. There's no other element present, and it is the hardest substance on the planet. Everything else comes below diamond. Notice we see topaz, which is a gemstone, quartz, which is a mineral, several other minerals going down the side there. On the right side of that scale, you can see common objects like a fingernail or a penny or a knife blade or glass. This can give you an example of how hard these different minerals are compared to everyday objects. For example, you can see quartz is quite stronger than glass, but gypsum is much softer. Cleavage. Next, on slide 27, cleavage is the tendency of a mineral to break on flat, even surfaces. So you could see quartz has very high cleavage because it's always breaking on straight lines. Those crystals are always straight. On the next slide, 28, we see an example. Mica has cleavage in one direction. Mica is a silicate, usually with, so it has silicon and oxygen along with an alkali such as potassium, an alkali earth metal like magnesium, and then a transition metal like iron or aluminum. All of these elements are in mica, and it breaks into sheets because of the way these elements are arranged. If you go back earlier in the presentation to slide to slide 14, we can see the different chains and sheets and the different networks of silicon and oxygen. Mica is always going to form a sheet, like the fourth example going down. Because mica forms these sheets, it breaks into sheets, and it has a what we call high cleavage. All right, let's move on to slide 27, or there, 29. Fracture. Minerals that do not show cleavage are, when broken, are said to fracture. Fracture is uneven breaking. And on slide 30 we see conchoidal, what we call conchoidal fracture. So notice this element does not break into nice even sheets the way mica does. Density is a property of all matter, the ratio of the mass to the volume. How much mass in a given volume. And of course, these are not the only properties of minerals. Minerals have many different properties because there are many different elements that make these minerals. Whether they are a silicate or a carbonate, they can combine with many different alkali metals, alkali earth metals, or transition metals in many different patterns. And because there are so many different patterns, there are many different properties. And as we saw earlier in the show, or earlier in the presentation, even minerals which are known by the same name can have different properties because the arrangement of the atoms is a little bit different. All right, so we'll end on that note. Thank you all, and I will see you next time.